Good afternoon, everyone. I'm Zhang Chao from Southeastern University. Today, I'm going to talk about predicting the yield stress of 3D printing mortar based on the flowability of paste and the excess paste thickness. Here's the outlook for my presentation. As we know, 3D printing mortar, as an emerging material, has attracted more and more attention. The number of projects involving 3D printing mortar increased sharply in the past 20 years. At present, 3D printing mortar is still in the initial stage of development. One of the fundamental issues is the mixed design of 3D printing mortar. Different from conventional concrete, 3D printing mortar need to have extrudability and buildability, which is governed by its yield stress, so it will be very helpful in the mixed design of 3D printing mortar. If the yield stress could be predicted on the basis of some characteristic parameters. According to the theoretical analysis on the relationship between the yield stress and the composites of mortar, the components of 3D printing mortar are divided into paste phase and aggregate phase. We choose the flowability of paste and the thickness of excess paste layer to build a model to predict the yield stress of mortar. We design 5 groups of paste with different nanosecond content and the same amount of aggregate to investigate the influence of the yield stress of paste on that of mortar. The mortar mix designs with the same aggregate content make sure the variation of the yield stress of mortar only results from that of paste. This slide shows the fitting relationship between the yield stress of paste and the mortar. The yield stress of 3D printing mortar presents a very linear relation not only to static yield stress but to the dynamic yield stress of paste. Aggregate content is another crucial factor affecting the yield stress of 3D printing mortar. To investigate the influence of aggregate content on the yield stress of mortar, we test the rheological behaviors of mortar with different content of aggregates. As shown in this slide, the rising of aggregate content leads to the increasing of yield stress of mortar. This slide shows the relationship between the yield stress of mortar and the aggregate content. We can see the yield stress of mortar is proportional to aggregate content, but with the rising of yield stress of mortar, the difference between the aggregate content in the two groups of mortar will decrease. In this case, it is difficult to establish a model based on the yield stress of paste and the aggregate content to predict the yield stress of 3D printing mortar. Given the excess paste layer thickness plays an important role in impacting the yield stress of mortar, the thickness of excess paste layer was selected instead of aggregate content as a vital parameter for investigating the influence of aggregate on the yield stress of mortar. The figure shows the fitting relationship between the yield stress of mortar to yield stress of paste ratio and the excess paste layer thickness. It can be observed the yield stress ratio is a power function of the thickness of excess paste layer, and the fitting relationship completes with the modified Cursor model. This slide shows the comparison results of experimental data and the calculated value in accordance with different models. It's obvious the modified Cursor model can provide a description of the relationship between the yield stress ratio and the volume fraction of aggregate. This indicates the modified Cursor model can be used to predict the yield stress of certain printing mortar. In the modified Cursor model, the yield stress of paste is an essential parameter, but the yield stress measurement for paste requires a real meter that is not a general device. In order to make the modified Cursor model more convenient to design the mix of printable mortar, we use an easier obtained parameters of paste flowability to replace the yield stress of paste in the modified Cursor model to predict the yield stress of mortar. The figures show the yield stress and the corresponding flowability of paste with different kinds and contents of rheological modifiers. We find there is a relationship between the flowability and both dynamic yield stress and static yield stress of paste, even though the cement paste contains different rheological modifiers. As a consequence, the yield stress of paste can be figured out in accordance with the flowability of paste. To further verify whether the flowability of paste is a suitable parameter to predict the yield stress of mortar, we measured the flowability of 3 groups of paste. According to the flowability and the relationship between the flowability and the yield stress, we can compute out the corresponding yield stress of paste listed in the table. Each group of paste were mixed with a certain amount of aggregate to prepare printable mortar samples, and based on the calculated yield stress of paste, we can figure out the predicting yield stress of 3D printing mortar, shown as calculated yield stress. The relative error between the tested and calculated yield stress of mortar is less than 13%. The results indicate flowability is applicable to be used instead of yield stress of paste to predict the yield stress of mortar. In this research, we can obtain the following conclusions. The yield stress of 3D printing mortar is linearly related to the yield stress of paste and aggregate content. The yield stress of paste and the thickness of excess paste layer can be used as 2 key parameters to establish a relationship based on a modified Cursor model put forward in this study to predict the yield stress of printable mortar. The flowability of paste is strongly linked to its yield stress even if the paste consists of different rheological modifying agents, and it can be used instead of the yield stress of paste in the modified Cursor model to predict the yield stress of 3D printing mortar. Thank you for your attention.